So, I'm reading this particular book called Reality is Not What It Seems by Carlo Rovelli, and this book has a lot of insights. And chapter 1 is a dissection of scientific thought, of scientific processes, and I wanted to encapsulate within 5 minutes what chapter is about. So the chapter starts by giving us a history of scientific thought, how it has evolved. So, roughly in 6th century BCE, in a place called Miletus, there were three people: Thales, his disciple Anaximander, and Hecataeus, who embarked upon a novel way of thinking. This was a thought process that reasoned. This was based on assumptions that people could agree and prove to be true, and not about former workings of theory that have been passed down from generation to generation. This was the first example of scientific thought. What they decided to do, and their first questioning of normal societal norms, is when they heard about the story of Heracles going to Cape Tenaro to find a gate to Hades, they decided to go and check it out for themselves whether this cape had a particular doorway to the underworld. And to be sure, they found none. And hence they concluded that this tale was false, even though this tale was widely believed to be true. And thus, the adventure of scientific thought began. Humans started to question things, and people started to believe in this way of thinking that questioned everything. So, some of the earliest discoveries were, we always thought that the sky was above the earth, because from wherever a human was, he or she would assume that the sky is always above the earth. But there would be another notion that would be proposed where earth was a globe, in which case the sky was both above and below earth, in which case earth floated in the sky in a certain sense, which is something that they proposed. Now, fast forward to 450 CE. The two philosophers, Leucippus and Democritus, they think of very novel things, and they write this book called The Great Cosmology, which talks about further scientific thought. But what Democritus would propose would radicalize thought in a certain sense for the next upcoming years, because he proposed that in little cosmology that basically there were very small particles that everything in this universe was made of. How did he come to this assumption though? That is what needs understanding. He assumed that if we have any random substance, one thing what he did was he observed real life phenomenon by looking at a wheel. A wheel rusts, and the iron degrades over time, the wheel corrodes it. Even a wooden wheel made during that time degrades and lessens in length as time progresses. Similarly, many other things naturally degrade over time. Why does that happen? He assumed that this is because everything that we see is made up of elementary substances, elementary particles in a certain sense. And how did he assume that there are elementary substances that everything is comprised of? Supposedly, you have a material. You can go continue to create smaller and smaller fractions of this. And his argument was that if I make infinitely small fractions of this substance, I would get what is increasingly a line, or within a 2D space what you would get is a point. And would infinite zero-dimensional points stack up to eventually produce a line? He thought not. And if a lesser dimensional substance cannot stack up to produce a higher dimension, then atoms also had to be 3D substances that had a finite size, that were not zero in their length, breadth, or height in a certain sense, and hence he inscribes some elementary size to them. Well, this is kind of relatively talked about in Zeno's paradox, basically, where he talks about this fact that Achilles has to travel supposedly X kilometers, and there's this tortoise who's traveling at a smaller speed than Achilles. And when Achilles travels, and this tortoise is actually placed at half the distance from Achilles, and the tortoise's speed is half of Achilles' speed. So when Achilles travels this much distance, the tortoise will have traveled 1/4 of the distance more. When Achilles travels 1/4 of the distance, the tortoise would have traveled 1/8 of the distance. When Achilles travels this 1/8 of the distance, the tortoise would have traveled 1/16 more. And hence, as Achilles tries to catch up, the tortoise is continues to move forward in smaller and smaller increments. And then, would Achilles ever be able to catch to the tortoise? This is a similar argument of breaking things down until you arrive upon something that is infinitely small, and yet it adds up to give a particularly integer-like value of, over here it would be 1. Sorry, it would be, yeah, over here it would be x, or if all of these were x by 2 and x by 4 and x by 8. So that kind of states our point that this contention is not foolproof. So what happens is, around 2300 years later, there's this young fellow who's 25 years old. His name, what most of you might be familiar with, is Albert Einstein. And his view of looking at things approached things in a similar scientific thought, but used a different argument. What he saw was, when suspended in sunlight, you see certain dust particles, and you see that their motion is very erratic. It performs what is now known as Brownian motion, where it kind of really jiggles around and wiggles its way through the air. And he proposed that if atoms were infinitely small, and basically the assumption is that they undergo motion because, as Newton puts it, motion is due to any force. And if atoms were divisibly infinite, and in a certain sense infinite atoms made up space, then each and every atom would have overall felt an average of, and throughout Brownian motion, forces kind of felt from both the left and the right hand side. So if the particles were truly infinite in size, then the forces from each and every direction, opposite directions, would be on average equal in number. And if we do that infinitely many times, they would in turn cancel out. And hence the net force on any particle would be 0, and hence an infinite amount of particles should result in no force. But we see forces. Another assumption was that, another way of looking at this was that if the atoms were too big, what happens if they're too big in size, right? You have certain forces that might move an atom, but then if they're too big and too few in number, then what happens is you have unrestricted paths of motion, where you will not observe erratic motion as you do, but rather motion of what a football might perform on a relatively empty ground. So he then correctly summarized that atoms were thus neither infinite or really few, and they had to be this size where they might have enough size to create forces that make dust particles move, not too large so that they completely overpower the dust particles, but also not too small that they don't have enough forces to impart upon the dust particles, in short. And the way he said that was because of the observed fluctuations in forces, we can conclude that atoms are finite in number, but not few and neither infinite.